everything down. I'm a writer. Like, I like to write everything down, and it stresses me when I can't. But I figured at least if you had those in front of you and I'm videoing too, you would be able to make do with what you need to do. So if we get to check our free responses today, that would be lovely, but I first want to cover content with you, okay? So you guys ready to be fast and furious? Yeah, fast and furious, here we go. Okay, so this is where we kind of stopped yesterday. We talked about how ideal behavior was going to mostly be attained at low pressure, spread out, and high temperature, really speedy. So what is ideal behavior? What does it mean they do? So really, really low likelihood of intramolecular forces. Remember, intramolecular forces are going to be London dispersion, dipole-dipole, and hydrogen bonding. And so those are reviewed. Now, how do I know something's polar? How do I know if a molecule's polar? What's a good example of a polar molecule? Okay, that's cheap. Give me something else. Smells like cat pee. Ammonia. Okay, ammonia looks like this. NH3 ... Those are lone pairs, right? Lewis dot structures from monoscan. These lone pairs have a good, slightly negative area of charge. This lack of electronegativity means these hydrogens don't want the electrons from their bond. They're pushing their electrons towards nitrogen to begin with because nitrogen's more electronegative. In the end, hydrogen has a good partial positive charge about itself. So this opposite end thing, opposite poles, means this is a polar molecule. Unequal distribution of charge. So if I'm a polar molecule, I can either undergo dipole-dipole interactions or hydrogen bonding. What qualifies it to be hydrogen bonding? Well, they're weak in biology, they're strong in chemistry. We're at such a nanoscale, biology thinks broader. We're at such a nanoscale comparatively strong. So hydrogen bonds have to have within the molecule a hydrogen bonded to F, O, or N. Hydrogen bonds are fun. Hey, hydrogen bonds are fun. F, O, N? Okay. So hydrogen is bonded to N in this case. So another ammonia molecule would be able to hydrogen bond with itself, right? So the hydrogen bond itself is not this bond, that is a covalent bond. The hydrogen bond itself is between this partial negative here. I kind of drew it off center, but this partial negative attracts to this partial positive like a magnet. This dashed line here is the hydrogen bond. It's not a bond, it's an attraction. Okay, so anyway, polar things usually have high intramolecular forces. All right, so we're assuming they don't. We're assuming because we want them to fit to connect molecular theory. That's not always the case though, because we do have some conditions that would not represent ideal behavior, so it's deviations from ideal behavior. And we got here, we talked about the A and B factors. The A and B factors are two factors that are used to manipulate the ideal gas equation. And the ideal gas equation, being P equals nRT, is excluding those because we're assuming ideality occurs. No volumulus particles and no intramolecular forces. But truly, the B factor, I'll start with the A factor. The A factor is the factor that relates to the ability of those molecules to attract to other molecules. So the A factor is the one that really deals with polarity. It also deals with the size of the particles, like bigger particles generally have more electrons, and more electrons means that they can actually shift their electrons around a little bit to create a slight dipole moment. They can be a tiny bit polar for just a moment, and then they can attract and then not attract. So that's the size does come into play a little bit, but it's really A for attraction. And if you remember A for attraction, then you'll be fine. So who's going to have the biggest A value? What kind of molecules? Meaning, if I say the biggest A value, who's going to have the most attraction? Polar or nonpolar molecules? Polar. Okay, so polar molecules are going to be greater in their A value than nonpolar molecules. And even within that, in that polar category, things that can attract via hydrogen bonding are going to have a greater A value than things that can attract via dipole-dipole. Because hydrogen bonding is stronger than dipole-dipole, which is sequentially stronger than things that have London dispersion forces. So we won't dig into identifying the types of forces too much right now. That's like in the spring, but I at least want to give you that feedback. So the A value is bigger in magnitude with the polar molecules. The B value is based on the size of the molecules, but it's more related to the volume they take up. We usually assume that they're volumeless, but they actually don't. They actually do have volume in a real gas. So B is going to be a correction factor for the volume. So this is kind of what I showed you last couple days ago. But we're not really going to memorize these formulas at all. We barely will even calculate with them, but you need to see the true one. Okay, right here. You have this on your paper, right? It's probably teeny tiny in your paper, but just highlight. This is just straight from your book. This is how we adjust the ideal gas law. By taking P and we add the attractive component, which is the A value. That A value, meaning attractive, we're considering how two particles, if I'm attracted to Avery here, I'm attached. I'm not going to bounce off the wall as much, right? She's not either, because we're attached to each other. We're basically attracted. So that pressure factor goes down. And then the volume itself, the volume that the gases have to play in is also lower than we think, because they are taking up a portion of their volume because they have volume. So it's just the correlation factors. At the very last page, slides, I think I have it next. Yeah, sorry, I have it next. I'm going to show you this first. You have this. These are called van der Waals constants, A and B. So let's go ahead and look at this as a data-based source. So looking at helium all the way down to ammonia, what do you notice about these A value? Who has the biggest ones? Who has the biggest A value? Okay, so ammonia does in this case because it's what? It is polar, and not only is it polar, but it is able to hydrogen bond. Okay, CO2 itself, actually the rest of these, CO2, H2, or H4, all of these are actually nonpolar. All of these have structures that have an equal distribution of electrons. Equal distribution means nonpolar molecules. All of these experience what force? London dispersion forces. So they all experience London dispersion forces. Actually, the ones with more electrons, like these bigger ones down here, they actually have a little bit of a stronger intermolecular force, London dispersion force. That's why they have bigger numbers. But not only that, what else did I say plays into the A value? Size, okay, mass, weight, right? So CO2 weighs 44 grams per mole, methane weighs 16 grams per mole, carbon monoxide, so the size, oh, no, actually this one's not polar. I missed that one, I was trying to look really quickly. This one's polar. My bad. And everything else is non-polar, yeah, okay. So generally, the polar ones are going to have the highest A values, generally, unless you are a heavy nonpolar compound, because you have a lot of ability for shifting your electrons in London dispersion forces. But basically, you can kind of see how the data correlates to that. The B values, they don't change a whole lot. This is supposed to be based on volume, but of course, these are all really tiny molecules. Helium has a pretty low value, neon has a pretty low value, hydrogen has a pretty low value. These are like the 0.02 ones. That's because they're teeny tiny, right? Everything else is bigger, so the values get bigger. That's from data standpoint. Kind of just shake your head, let me know we're okay. Okay, maybe not good, but okay. Okay, so back to, oh, this is the only other part. I'll just show you the graphs. They like to give you a lot of graphical analysis to make you think about the data that you're pulling from a graph. So the deviations from ideal behavior, this is the ideal gas line right here. And so you can see deviations from ideal behavior at, you see the pressures down here, at high pressures. High pressures means you do work your volume. Squish them together, right? Squish them together like, hey, attract. So they start to deviate because of attraction components come into play when they're closer together. Yeah? Okay? And then over here, the ideal behavior is supposed to be right here, at this line right here. You can see this is the temperatures. This is at 203 Kelvin, 293 Kelvin, and 673 Kelvin. We have the most deviation from this flat line at cold temperatures. So they're slowing down. They're starting to have time to interact. Okay, so I think I've kicked that horse enough. Can I move on? Calculation. This is the kinetic energy stuff I had on the board yesterday. I didn't get a chance to talk about it. There are two kinetic energy equations. One is for average of an entire sample of gas. One is for an individual gas. So you saw this one on your video from Monday, yes? What's the R value again? 8.314. You have to think energy, joules per mole Kelvin. Okay, so don't forget that's your R. That means temperature must be in Kelvin. And the relationship between kinetic energy and this equation should definitely be that joule right there. Because the kelvins will cancel, right? Running units is important. You'll have joules per mole, which is going to be representing your average kinetic energy of your sample of gas. Okay, oh, so how is this depicted on the Maxwell-Boltzmann curve? That's why I left all this space here. I'll draw right here. You have your Maxwell-Boltzmann curve, your average kinetic energy, will be related to where most of your gases are taking, or most of them are at a specific speed, which will be in the middle part of the bell curve. Okay, so that's one equation. Make sure you write average there. The other one is kinetic energy is equal to 1/2 mv squared. Who's heard this one before? Physics, maybe? Physical science, middle school? I don't know if you guys are in small school. Okay. So this is related back to the mass of a particle and how quickly it can move. Big molecules can't move very fast. Small molecules can move really fast. So we're talking about those differences in speed, right, of a sample that's bigger, mass that's bigger or smaller. But we're saying it equals the kinetic energy. So truly, every particle at a specific temperature should have the same amount of kinetic energy. Does that mean they have the same speed, though? Doesn't mean they have the same velocity. Just means they have the same amount of energy embedded. So energy can be related to force. So like force of impact. If I really just lightly bump into Avery, okay, I'm not going to hit her with a lot of force. I'm moving pretty slow. But if I'm a big molecule, that force might have an impact than it looks because of the mass behind it. So that's why the kinetic energy truly is equal to this specific temperature. This is at a temperature in Kelvin. Okay, so generally you'll see this inverse relationship. Increase in mass means velocity goes down. And decrease in mass of a particular gas molecule, velocity goes up. But overall, how does this look on a graph? You've seen this graph. You have molecules down here that move. They can move slower, they can move faster, and then your average, of course, here is in the middle. This could be a mixture of gas particles moving at different speeds, or if you think about it in terms of temperatures, you can make it different as well. Really, they have to describe to you what this graph is representing. Your differences in temperatures would be like this, or like this, with your peaks all different because of differences in temperatures. They'd have to describe it. I have a couple of examples in a bit. Okay, so last thing with this part, because the equation is a little different, you have kinetic energy is equal to 1/2 mv squared, right? Well, m is going to be mass, but in this case we're talking about kilograms. V is related to speed. Velocity is not necessarily speed, but velocity is a rate per time. So is a distance per time. So we have meters per second, but this is squared, so it's meters per second squared, right? So this right here is a weird unit, but all together it equals a joule. Hence why kinetic energy is equal to this crazy unit here. So it is still a unit of energy. It is still joules. This is something you would do in physics more than anything with newtons. Okay. Calculation. So you guys have this on your sheet of paper, but in terms of calculating, we briefly mentioned that there was something called root mean squared velocity, where you'll see this in your textbook, where the particles, when they move at a specific velocity, it is indirectly related to their molar mass. So if it's indirectly related to their molar mass at a particular temperature, you end up getting this equation. Root mean square velocity is equal to square root of 3RT over m, where m has to be in kilograms. So it is inversely related. What you'll start to see is that we can actually put two of these speeds together, these root mean square velocities together, as a comparative, and that's Graham's law. In Graham's law, we compare two gases. It's just really this together smacked on top of each other. So we're comparing velocities in that respect. And again, our R constant is the R constant that relates to energy, and then our combination of factors where we have, bless you and stuff, where we have kilograms involved, it is just through the relationship that kilograms times meters squared over seconds squared, that together equals a joule, which again relates to our energy component. So I'm actually going to solve the problem with this right now, because I think some of you guys got to it on Monday too. Okay, so this is where, I think the next two slides, I'll come right back to this actually. Here, okay. So there is some mathematics. I'll show you. There's a proof. I don't really want to proof it. Well, I will first say velocity makes sense to be in meters per second. Yes, it's a rate. So it does make sense to be meters per second. So please don't forget, use your brain. Make sure your units are correctly expressed. But the proof, we ain't got time for this right now, but the proof does relate how on with a constant with Avogadro's number, another constant, that's the K constant from the Boltzmann Maxwell-Boltzmann curve, and then which is right here, and then temperature. And we don't need to know how to derive it ourselves. That's just a good thing for your free time. You know, when you have free time. But we're gonna plug this in right now, okay? So we're gonna plug this in. So using your root mean square velocity, let's find the molecular. Let's not find the velocity of molecular chlorine. What is the root mean square velocity formula? 3RT over mass in kilograms. Okay, what are the particular variables? So 3, what's R? 3R, okay. You guys are writing this down for yourself for a sample problem for later. 8.314 joules per mole K. Temperature in this case? 293, thank you, Kelvin. Molar mass in kilograms of chlorine gas. Say again? Chlorine gas. 0.07, thank you, because it's 70.9 grams per mole, so 0.07090 kilograms per mole. So it's just, we're basically taking the grams and bouncing the decimal back 3 spaces and calling it kilograms. This is still appropriate with the mole here. All right, so knowing that, what units cancel? Kelvin, I hear, and moles. And we're gonna get, we have joules per kilogram right here, right? Is that it? Yeah, okay. So in this case, the calculation is, oh, sorry, I gotta show you this first. So we can calculate, I'm gonna go ahead and write the units first. So joules, like I said earlier, was what broken down? Kilograms times meters squared over second squared. So that's the joules right here. And all that other stuff got canceled. And the only thing we have left on the bottom is kilograms. Okay, so what cancels here? Kilograms. So when we square root meters squared over second squared, what do we get? Yay! Okay, so we have meters per second. So that is our proof of how velocity is related to all this nonsense. What's the number though? Anybody? 321. Wonderful, guys. Oops. 321. So this bad boy is moving at 321 meters per second. Holy cow. Is that fast or what? Pretty dang fast. Okay. So if I take a chlorine molecule and release it, I throw it at Binky, is it really going to get to him at that speed of 321 meters per second? No. Why? There's a bunch of stuff in the way. All these gas particles, it actually has to go through, oh, I forgot the name. Hold on. Oh, Brownian motion. Gosh, I had to think about that. Brownian motion is this guy who described diffusion, basically, Mr. Brownian. And this particle has to bounce off all these things in the way to get to these. You would smell it and you would die because my gas is closed down. But in this case, it could travel at this speed and not with anything in between it. But it's definitely not traveling at that speed because of interference. Cool? Moving on. Okay. So, oh, I wanted to go back to those graphs for you. So, like I was saying earlier, the Maxwell distribution curves can be related based on compound or based on temperature or a combination of both. And so this someone has all oxygen at different temperatures, and you can see how the graph has shifted to be have more range in the 2000 Kelvin and much less range in the 273 Kelvin. And this is talking about all oxygen. But you could create a graph with different compounds to talk about their different speed distributions as well. But I could give you this, and I could take away these numbers, and I could ask you based on the graphs, graph 1, 2, or 3, which one has the highest temperature, and you would definitely know it's 3 because of the range that is there, and the maximum terminal speeds that are over here, which are much higher, and their average is higher than these here. So you know that's correlated with temperature. So that's a good multiple choice question you would see there. Okay, so I have one more calculation. Oh, I kind of just showed you that. temperature 1, temperature 2, which is greater. Temperature 2 because the higher average. I'm not sure what just happened there. Higher average. Okay, and then I got to get to grams here. So we talked about grams a teeny bit yesterday with the FRQ we reviewed, and that was when we were talking about the ammonia in one end of a big glass tube. I'll show you the picture of that actually first. Right here. So this is like actually the glass tube. I thought we could maybe do that lab in parallel with our other lab from yesterday, but we didn't. So this is one end of the tube, this is the other end of the tube. You soak cotton balls, you stick them in the ends. One's soaked with ammonia, concentrated ammonia, and one's with concentrated HCl. Why does the formation of that precipitate, which is ammonium chloride, why does that form right here closer to the HCl side? Does it move faster? Why? Okay, because it's lighter, so lighter things have a greater velocity they can take on. And so this is the relationship between the root mean square velocity and Graham's law, where you are comparing the root mean square velocities of two different gases. And since the root mean square velocity is equal to square root of 3RT over the molar mass in kilograms, and then you compare it to this one, so you're dividing square root of 3RT over the molar mass in kilograms. What you'll notice is that there's some commonalities here. What can cancel? 3RT, because it's at the same temperature, right? We're talking about the same temperature. 3RT can cancel, 3RT can cancel. So then you're stuck with square root of 1 over molar mass of ammonia over square root of 1 over the molar mass of HCl, and then you do that floppy dot flop, multiply the top of the numerator's this thing. Yeah, you know what I'm talking about. You know what I'm talking about? Okay, square root of molar mass of HCl over the molar mass of NH3. So that's the proof of how we take our root mean square velocity into Graham's law. But nobody wants to do that proof every single time. You memorize Graham's law, right? And we've memorized Graham's law probably by default from honors chem, but Graham's law is actually this right here. And whenever you're trying to plug these data points in, you do have to think about, am I putting the right one on top? Because it doesn't make sense to go, yeah, Sean, he's 0.25 times faster than me. Is he? 0.25 times faster than me? That means you're a quarter of my speed, right? That means that you're slower. So it doesn't make sense to talk about something being faster in terms of like a decimal. So if I said Sean is 1.25 times faster than me, that makes sense because he is truly faster than me. Don't be misleading with how you report your data. So you always put the lighter gas as gas A in your setup so that when you see this inverse relationship between the rate and the molar mass, you see that they're inversely related, it makes mathematical sense when you state it in a statement. It just helps make sense of it. And then gas B, of course, is going to be on top of the molar mass fraction. Okay, so using Graham's law, can I go forward? Using Graham's law, let's go ahead and find who the unknown in this first example is. And let's talk through this because we got to go forward. We get out at 9 o'clock. Okay, great. So, at a given temperature, an unknown noble gas travels at 1.26 times faster than oxygen gas. What's noble gas? Who's faster? Okay, so the noble gas is traveling faster than oxygen. Okay, so who's lighter? The noble gases. Okay, so rate A will be the noble gas, and rate B will be the oxygen gas. Don't forget, oxygen gas is diatomic. Don't make that silly mistake. And so the rate of noble gas versus oxygen is 1.26. But that rate is equal to their molar masses, the square root of their molar masses. Whose molar mass do I put on top? Oxygen, because it is an inverse relationship, right? So oxygen goes on top, that's 32 grams per mole. And the noble gas's mass goes on bottom as X. What do you do to solve? Square both of these. That's like 1.5876, something like that. And that's 32 over X. So what do you do to solve for X? X is equal to 32 divided by 1.586. Chloe, you got me? Did you do that calculation?
No.
Is that right? Did you do 1.26 squared? 1.2 squared? 1. Yeah. Okay. So what is it? What's X? 20, say again? 20.16 grams per mole. Don't forget your units. What noble gas is that? Neon. Okay. So these would be easy questions, I think, to get right in terms of multiple choice mathematics and free response. Because free response is kind of clear. But multiple choice, I really do try to make the math easy. So, I mean, I could do something like square root of 4. We know the square root of 4 is 2 and so forth. Or squaring something, that would be like 4 squared is 16 and then backtracking. So I really am not trying to kill you on that mental math. All right, compare the rates of diffusion. Now this is phrased differently, but it's the same concept. Compare the rates of diffusion of carbon dioxide and oxygen gas at the same temperature. You guys do that one. I'm not going to think about what we're doing. What are you guys putting on top for your rate A? Say again? Oxygen, why? It's lighter, okay. Trying to do that in my head. Thank you, what you got? 1.7, okay. Oh, 1.17? Okay. All right, can you put that in a sentence to describe what this question is pulling together with this answer? So oxygen's molecular velocity is 1.17 times faster than CO2. Cool, yeah.
You also say
So, because it does say rate of diffusion. Rate of diffusion and rate of effusion are very similar. I quickly did skip that. Did you guys capture that? Rate of effusion versus rate of diffusion? Diffusion is kind of like just traveling in space, not really in a particular area. Effusion is taking place through a pinhole, like in a vacuum. But usually I use this example like with a balloon. So using that logic, carbon dioxide versus oxygen. If I had a balloon for my birthday next week, and I had some gases in there, what gas would stay in there the longest? So who, in that case, oxygen or carbon dioxide? Carbon dioxide. So if I really want a birthday balloon that lasts, until next semester, blow it up with your mouths. It's okay, we'll just tape it to the wall. It don't have to float. Just take it to the wall. It'll last, carbon dioxide lasts a lot longer than helium. Helium weighs what? 4 grams per mole. That's why it's gone within 72 hours usually, because it infuses very, very quickly relative to its other counterparts. So helium's is overrated, and it's also endangered. We're running out of helium. There's a big reservoir of helium under Texas, I think. We have like a big storage house underground. We're almost out. So helium cost, I don't know if you've noticed, I don't know how often you get birthday balloons, but it's gone way up in the past like decade. So helium's in danger. Fun fact for the day. Okay. Fun fact for the day. All right, last thing. You guys have, oh, do I want to show you that? No. Oh no, I didn't want to show you that. All right, this was my last example of the Maxwell-Boltzmann that I was trying to show you earlier, where it has different gases, not different temperatures. So you see how Maxwell-Boltzmann can be used in maybe 3 or 4 different ways. This one has our speed still, but it's relating oxygen to methane to hydrogen. So why is hydrogen the one with the maximum terminal speed? It's the lightest, and this is all happening at the same temperature. So at the same temperature, which is correlated to the same kinetic energy, right? Kinetic energy is equal to 1/2 mv squared. Truly, hydrogen gas being the smallest means that the terminal velocity would be technically the highest. Yeah. For this one, I don't know. This one might, it should be because we should be comparing a constant. The only variable of difference is the identity, but it doesn't look very much like it, but it could be. I'd have to like do the integral, right? So, but this is supposed to be hydrogen's average speed versus methane's average and oxygen. Truly, the averages for the same the average speeds for the same kinetic energy should be the same. It's talking about the different gases in this respect, so the terminal is actually a lot faster. So, do me a favor. I want to walk through. We have about 20 minutes left. I want to walk through. There's a little half. Looks like this. Looks like this. I think I printed this in your packet. If not, we'll walk through these on here. Is it in the packet? Okay. I want you guys to get acquainted with this without losing it too much. Because I know that these are probably the harder ones compared to like previous people on our team. Yeah. And I want you guys to do just a couple of these. Not many. You guys can pick and choose the ones you do. But I want you to just maybe get 10 minutes of practice in right now. So I printed in there. Oh, that's my copy. That's why. You know what? Yeah. I was upset. This copy is for myself. I can find it. It's in your pocket. It's teeny, teeny, tiny. Under the motion, over here. So just pick a couple and do those right now. Don't be spoiled because I have the big one.
Okay, so the that's just one. And then they approach so when the mass is less. Yeah. So usually it's less. That means it's a percentage. Yeah. So the maximum speed is the world axis, right? Oh, so that's it.
A lot of these variables. All right, which one are we doing? Uno, two? Okay. Okay. Well, I feel like Speedy Gonzalez right now, but we're gonna go over our FRQs as well. Oh, I need to see FRQs. Have free response 4 and 5 on his best. That's all we're doing. I'm gonna go over today.
these classes.
I'm gonna pull up that answer sheet here. Yes.
On my test? Oh, no, I can't. Yeah, no. I didn't know how to do anything. Except for, like, I knew how to do a math tree. But, like, oh, no, I was not. See, but you're saying you got so many, like, 80s or 90s, and I'm just like, well, and then I get a 40.
Flash means we're in Texas. So it helps me on for if I don't get to the meeting, I actually thought I should have Sean got it. I guess. No, it's just more.
What? No, that one. Okay, what did you get for the rest? What did you get for
As long as that makes sense. Okay. Alright, so let me just quickly hit number 1 and 2, and then we're going to jump off this one. 1, what equation did you use to calculate average kinetic energy? 3/2 RT. You plugged in the different temperatures, and you got, boom, done. 2, what equations did you use to calculate room mean square velocity or root mean square velocity? But I put room. Okay, what did you guys use? Square root 3RT at that particular temperature, 273, and then 546, and what else? What other unit was there? Divided by the mass in kilograms, right? Okay, and then number 3, what equation would you use here? So when you say R, you mean rate?
Yeah.
So what equation is that?
The grams.
Graham's law, that's the comparative rate one. And if you're doing only half, like if you're not doing the comparison, you can still do the same thing. It's rate A is equal to 1 over the square root of its mass. So you could do that. And then 4 is a lot more involved. But 5 is Graham's law. 6 is a good question, just in general. 6 is a good question. Okay, that was just a comment I want to make. I have about less than 10 minutes left. I got through part C yesterday on question 3. Yes? Question 3, FRQ. So, combustion analysis makes a comeback. Right? Did you guys see number 3 had combustion analysis in it? Give me some feedback here. No? How did you guys do number 3D? Okay, so I think we got through yesterday. Did we get through this? My bad. I'm sorry. Yeah, this is 2. Did I only make it through 2 yesterday? No? Did I make it through this? I think I only made it through 2. We were at the qualification of determining how many Q's were in the compound. Work with me, you people. Work with me. We got 19 grams per mole. Give me a thumbs up if you made it to 2C successfully there. Alright, in part 2D, combustion analysis makes a comeback. Okay, so that's where we had a specific amount of carbon dioxide made, water made, and you had your grams of your Z compound, which had Q, carbon, and hydrogen in it. And so that, to me, I don't know if you saw that, but it screams at me combustion analysis. Did anybody else see that? Okay, so it's empirical formula with combustion analysis where you take your carbon dioxide and your water to their individual components of C and H. So 0.0311 moles of carbon, 0.0321 moles of hydrogen. You had to get to your grammages because you got 1 gram of your compound original. So if you get your grams there, you can subtract from your 1 gram original and get your component of Q. And the mass of Q should have been about 0.595. And so since previously in part C you knew the molar mass, you were able to obtain the moles of that. And just like any empirical formula, you compare moles to moles to moles. Whichever is the lowest moles, you divide. And with respect to all of them, they were basically the same, so it was a 1-to-1-to-1 ratio. That was for the empirical formula. But then, since the empirical formula mass total was 12 plus 1 plus 19, that was 32 grams per mole as the empirical formula mass. And the total mass of the compound from the table was 64 grams per mole. Those two component, or two being your multiple, your molecular formula mass would have been C2H2Q2. Give me a thumbs up if you made it through that process. Okay, where did we get stuck?
So it's like the missing element of oxygen. You can see CHO. Then like you can see industrial analysis.
So it says it was burned, right?
Yeah.
Or it's oxidized, meaning oxygen was a component. Because despite the fact that oxygen's not the approved formula, the process still worked out where you're not really doing it with respect to oxygen, because the oxygen could have been the O2 that was combusting with it. So you took away from your original compound, your 1 gram, you took away the components of it. So the process is still the same. I'm calling it combustion analysis, but we're not analyzing it for oxygen. Okay. Okay, so that's 2. 3, this was the one that's very similar to your lab, where you had your sample collected over water, calculate the moles of hydrogen gas collected. So just like in your lab yesterday, you took your gas total, your total pressure, which was atmospheric pressure 475, minus your vapor pressure, which was given to you in the problem, got your gaseous pressure, took your gaseous pressure, divided by 760 to get to atmospheres, used your PV equals nRT equation, you should have gotten 0.00349 moles of hydrogen. You have one very, very similar to this on your test. Okay, very similar. So in terms of getting the moles of hydrogen, we should be good there. How many sig figs should there be? Was it 90? Sorry, 90.0 was our qualifier sig fig, so it should have been 3 sig figs. So 0.00349 should be it. And they do, and this was a good question for another group, on the FRQs on the national exam, we do count sig figs. They do count units, and usually if you mess up on sig figs or units throughout the problem, they just take off 1 point off the top of your entire FRQ. And if your FRQ is only worth like 10 points, that automatically drops it down to 90. So do try to have like a moment of reflection at the end and go, did I do correct sig figs? Do I have my units everywhere? Okay, so then your other question was converting moles of water, solving for moles of water using the same exact setup, but I did this with respect to water's pressure, and you could get your moles of water being 0.000115. Did anybody do that differently? You couldn't, because it's not a reaction, right? There's no way you could have done a mole to mole ratio. So that's why you had to do it this way. Okay. And then second one was using Avogadro, or second part of this was using Avogadro's number to get to molecules, 6.94 times 1019 molecules. Give me a little head shake, a little nod, something like that. Thank you. Okay. And then part C, which was what we just learned today. Sorry guys, trying to get through content with you. Ratio of the average speeds of the molecules. And again, in physics, speed and velocity or calculus, those are 2 different things. In chemistry, a lot of times they're used interchangeably. Speed and velocity are very similar for us, because we are talking about molecules at this point. And so when you plug in your Graham's law equation, using the water and the hydrogen gas, hydrogen's lighter so it goes on top. When you put your information in, you get hydrogen moves 3 times faster than hydrogen moves 3 times faster than water. It's supposed to be H2. Sorry. And then lastly, part D, which of the 2 gases, H2 or H2O, deviates more from ideal behavior? Which of them is polar? H2 or H2O? H2 is polar, right? H2 is nonpolar. So first of all, whenever you do a free response question, this is for my test, but I really try to grade it so that you're understanding your requirements. If it asks for 2 things, it asks you to compare 2 things, you must mention something about both of them. Don't say, water's polar so it deviates more, because then you totally disregarded H2, right? Obviously you know what you're talking about, but you're not portraying it fully. So say, water deviates from ideal gas behavior because it's polar, and then secondly, H2 is nonpolar. H2 is nonpolar and experiences London dispersion forces, which are weaker, so it's not going to attract as much. So you just must mention both of them to get your 2 points there. Not just mention them, but explain both of them. Okay? And then I have no time, so what I'll do, guys, is, circle this on your work, on your packet now. 1990, it's already online. 1999 multiple choice, it's right above what you were working on your genetic multiplication video. I am putting a Socrative quiz online for studied evidence.
after the quiz will be online for study evidence, it'll be open. And you're doing unit review, so the two assignments are multiple choice and unit review, multiple choice and unit review. Please allow me to in my room when they are complete. I will give you So, guys, I have meetings at 11:15. I'm trying to get you a place to stay. This is summer. There's a way you can stay someplace. I'm going to be in my room. Slept in my room. Totally by cheaper. Bye.
You're coming back at 1. Are you going to be here?
I don't know if I'm in meetings at that point. I'm from meetings from 11:15 to 2:30.
Can I just slide
Slide
in the
something
door?
under my door. Yep.
So, the simulations, they weren't